All right, so back to the not so fun part of probability. More probability rules. Let's see. Having fun playing with the birthday problem? Okay, good. All right. So, more probability rules. We'll do another rule for OR. The rule we did yesterday for OR was if we have mutually exclusive sets. Well, not every set's going to be mutually exclusive, so we're going to need a different rule for ORs. So let's start off like we did yesterday. We're going to say event A is rolling a 2 on your die. Event B is going to be rolling an odd number. Ruling an odd number. And what are the outcomes for that? So now I'm going to add event C that's not going to be disjoint. I'm going to say you're going to roll a number. Roll a number greater than 3. So what are my outcomes for that? All right. Are set A and B disjoint? Set A and C disjoint? They have any outcomes in common? No. How about set B and C? Are they disjoint? Set B and C are not disjoint. So if I want to find the probability of A or C occurring, we write that as the probability of A. Oops. That was an and. Or C. That's going to be the probability of getting a 1, 3, 5, 4, 5, 6. We've got a little repeat going on here. So that'd be the probability of getting a 1, a 5, a 4, or a 6. Oh, geez, B. Sorry. I wanted the ones that were disjoint. Sorry. God. Crazy. There we go. All right, so what do I want the probability of B or C to be? What number do I want it to be? What number do I expect it to be? 1, 2, 3, 4, 5 out of 6. Okay? But if I took the probability of B and added it to the probability of C, probability of B is 3 out of 6. Probability of C is 3 out of 6. That's 6, 6. That's too much. I got to take some off. And what am I going to take off? I'm going to subtract the outcome in common. So the probability that B and C occur. And the outcome in common, there's one outcome, so that's 1 out of 6. So this gets to be the 5, 6 that I had hoped it would be. Yes, it always is. This is the general rule because it works for disjoint and intersecting sets. Yeah, the general rule works just fine. Just as I'm going to give you a general rule for and today, and it'll work for everything too. Yes, ma'am. Oh, so the probability that I get an odd number and greater than 3. There's only one of those that qualifies as an odd number and greater than 3. That's the number 5. So that's one outcome out of 6. Okay. Moving on to conditional probabilities. That was just another rule for so what should we call this one? This is an addition rule. That's what it's called. So this is the general addition rule. Can't write. ENERAL, addition. Rule, or the general rule for ORs in probability. Okay, I'm going to define conditional probabilities. So a conditional probability, if I have an event A and event B, I want to know the probability that event A happens if event B has already happened. I write that as the probability of A, big line, B, and I read that as the probability of A given B. It means the word given. And I'm going to define this probability of A given B as the probability of A and B divided by the probability of B. And this conditional probability is going to go back to those tables that we did before when we talked about conditional distributions with the two-way tables. So let me do a two-way table, but I also see now a different equation for A and B. Do you see now a different way to figure out A and B? Multiply both sides of this equation by the probability of B, and you get the probability of A and B to be equal to the probability of B times the probability of A given B. And because of the commutativeness of this intersect feature, why am I back to birthday problem? I don't know why. Oh, I think it put this page in the wrong place. Also, the probability of A and B can be the probability of A times the probability of B given A. Okay, may need this somewhere in life, so. Oh, sorry. Trying to figure out where all my pages are now. Okay. We'll leave that one up for a minute. And we'll do a little example using the two-way table.